Happy learning! Today we're going to talk about touring a graph. Okay, so let me start by drawing a graph that we're going to use as our running example for today. So let's let G be the graph that has 7 vertices. That looks like this. All right, and so this will be A, B, C, D, E, F, and G. All right, and we're going to talk about ways to travel along the graph. Okay, so we'll start by defining what a walk is. So a walk is a sequence of vertices such that there is an edge between consecutive vertices. All right, so let me give you an example of a walk. So for example, maybe we start at A. And so the next vertex has to be one that's neighbors with A. So it could be G, F, or B. Maybe it's B. Now we're at B. And let's say we go down to F. And maybe we travel back to A. And back to B. And then finally to C, right? So A to B to F to A to B to C. That's a walk from A to C. All right, so a walk is just basically you can't teleport. You have to make sure you're traveling along edges. Okay, a closed walk needs to start and end at the same vertex. All right, so the example that I just drew is not a closed walk, right? It starts at A, ends at C, which A and C are not the same vertex. All right, what's next? A trail is a walk with no repeated edges. All right, so the walk that we drew here certainly is not a trail because we went on the edge AB twice. So an example of a trail would be something like A to G to F, back to A to B to C. All right, so here we did repeat the vertex A, but we didn't repeat any edges. So this is a trail. A closed trail is called a circuit. Okay, so walks and closed walks go together, trails and circuits, and then finally a path is a trail. All right, so a path automatically has no repeated edges, but it has the extra condition that there are no repeated vertices. All right, so this example here, of course, is not a path because A is repeated. So let me give you an example. A to G to F to B to C, that, of course, is a path. Okay, if we have a closed path, so we start and end at the same point, we're allowed to repeat at that one starting and ending point, but that's it. In a closed path, is called a cycle. All right, so trails and circuits go together. Paths and cycles go together. The length of any of these tors is the number of edges. It's not the number of vertices. Okay, so the length of this path here is AG, that's one edge, GF, 2, FB is 3, B to C is 4. Okay, so the length is equal to the number of edges. All right, so we got a lot of vocab. So let's look at an example here. I'm going to keep our graph because we're going to be using this today. All right, so let's say here's an example. After I write the example, just pause the video and try it on your own, right? Learning is not a spectator sport. You got to get in and work the problems before you watch me solve it, all right? So let's find a cycle of length 4 on the graph. All right, so please try this on your own. Your answer might not match mine, but I'll show you how to check your answer, right? We need a cycle is a path that starts and ends at the same point. So we just make sure no repeated vertices, and then the length is the number of edges. All right, so my answer is maybe we start at A, and we go to B. That's one edge. Then we go to F, down to G, and then cycle back to A. All right, and so you can see on the graph, A to B, B to F, F to G, G to A. We start and end at the same point. We didn't repeat any vertices, and the number of edges was indeed 4. So this is a length 4 cycle. We did it. Okay, great. I know it's been a little bit vocab heavy these first few lessons, but we got to get the language locked in so that we can start solving some hard problems. All right, so we're going to define now what it means for two vertices to be connected. All right, you might think the natural definition of vertices to be connected is if they share an edge, but we already said that's what it means for them to be adjacent. All right, so we don't want a definition that we've already used. It's going to be a little bit more general than that. So let G be a graph. So here we have some graph. Maybe if you want to think about it, we could use this as an example. Two vertices, X and Y, are connected If what? There exists a path from x to y in our graph. All right, so for example, G and C, even though there's no edge between them, they are connected in our graph because you could go from G to A to B to C, and that's a path that connects G and C. We say the graph is connected if every pair of vertices are connected. All right, and so we could check that this is indeed a connected graph because you take any pair of vertices, you could find a path to get from one vertex to the other. Now, if we had an eighth vertex over here, which maybe we call H, this graph would no longer be connected, right? There's no way to get from E to H traveling along edges. All right, so you could see if a graph is connected basically by looking at it typically. All right, let's work through an example. So let's let G be the graph with vertex set A, B, C, D, E, and edge set AB, AE, BC, CD, DE, EA, and EB. All right, so here we have the vertex set and edge set notation for our graph. We don't have our drawing yet. And what I want us to answer is our graph connected? All right, and it's not immediately obvious from our vertex set and our edge set if our graph is connected. So think for a second, how can you check if this graph is connected? All right, and so what I would do is I would draw the graph. All right, let's draw this graph, and we'll see, is it connected? All right, so what does this graph look like? This graph has 5 vertices. We could lay them out however we'd like. With 5 vertices, I kind of like to lay them out kind of in a circular pentagon shape. So let's say here's A, B, C, D, and finally E. And now we want to include our edges. So AB, AE, BC, CD, DE, EA. So we actually have a multi-edge here, and EB. All right, so the question was, is our graph connected? And you could see, yes, it is connected. No matter what 2 vertices you pick, you could always find a path from one to another. All right, and so what we're going to talk about now is we're going to look at specific types of trails and circuits where we cross every edge exactly once. So this is named after a very famous mathematician by the name of Euler, his name is written like you would want to pronounce it Euler, but it is pronounced Euler. All right, so an Euler circuit or an Eulerian circuit, you hear both. Okay, so what is an Eulerian circuit? Well, of course, it's going to be a circuit. What is a circuit? It's a closed trail. What is a trail? No repeated edges. So an Euler circuit or trail is a circuit or trail that contains every edge and vertex of the graph. Okay, so it's a circuit that contains every edge and vertex. So we cross each edge exactly once. Okay? It's possible that this is impossible on some graphs. We'll have a way to check. If G contains an Euler circuit, all right, let's an Eulerian circuit, then we say that G is Eulerian. If G contains an Eulerian trail, then we say G is semi-Eulerian. All right, and we're going to see in a few minutes that there's a very easy way to check if a graph is Eulerian or semi-Eulerian or neither. All right, so let me give you an example of some graphs. So for example, suppose we had the following graph with 4 vertices. Okay, can you find an Eulerian circuit on this trail? Yeah, it's very easy. Just travel along, basically make a big old cycle, right? So this, if we travel in this direction, we cross every edge exactly once, we hit every vertex. This is Eulerian. Okay, this graph we can't cross every edge exactly once and start at the same point, no matter how hard you try. So there's no Eulerian circuit, but there is an Eulerian trail, right? If we start here and go to here, we hit each vertex and edge exactly once, right? So why is this a trail, not a circuit? Circuits have to start and end at the same point. Trails do not. Okay, so this is semi-Eulerian. All right, and then one last example is suppose we had a graph that looks like maybe a star. Okay, I know what you're thinking. What kind of star is this? Not exactly sure, but suppose this is our graph. Is it possible to start and end at the same point without doubling up on an edge? No, it's not possible. And no matter how hard you try, you can't cross every edge exactly once. So this is neither. All right, so it is possible for a graph to be Eulerian, it's possible for it to be semi-Eulerian, and it's possible to be neither. All right, and so the theorem that we're about to state will tell us exactly when we know a graph is Eulerian, exactly when we know it's semi-Eulerian, and then anything else would be when it's neither. All right, so this notation here, them, that means theorem. It's like a mathematical fact. And this theorem is the test for Eulerian. All right, so it's very simple to check if a graph is Eulerian. The theorem says a graph G is Eulerian if and only if. It's the only possible way this could happen. If these two conditions hold, it's Eulerian. If one or both fail, it's not Eulerian. That's what if and only if means. First condition, G is connected. All right, if there's disconnected parts of the graph, there's no possible way we're going to be able to get a circuit that goes to the disconnected components of the graph. Remember, we always have to travel along edges. So our first is G is connected. The second condition is every vertex has even degree. You could check in our graph here, which is Eulerian. It's connected, boom, first thing, easy. Check the degrees. 2, 2, 2, 2. 2 is, of course, even. All of these vertices have even degree. It's Eulerian. This graph is not Eulerian. That's degree 1. The first vertex is degree 1, which is odd. All right, so this is our way. This is how you check if the graph is Eulerian. And these are very easy things to check. A graph is semi-Eulerian if and only if. All right, again, if one or both of these fail, we know it's not semi-Eulerian. If they both succeed, it is semi-Eulerian. First condition. Tell me if you've heard this one before. G is connected. Second condition. G has exactly 2 odd vertices. All right, this graph here has degree 1, degree 2, degree 2, degree 1, has 2 odd vertices. It's semi-Eulerian, right? We didn't even have to find the Eulerian trail in order to show that it's semi-Eulerian. This theorem tells us, since it has exactly 2 odd vertices, we know it's semi-Eulerian. Okay? And so in the previous video, we talked about the Königsberg Bridge problem, which is where we had the city of Königsberg and we wanted to travel across each bridge exactly once. Okay? That question can be restated as find an Eulerian circuit or trail on this graph. So let's look at the graph that we had. Right? We had this is our graph of Königsberg. Right? We took the map, and each of these vertices represented a region in the map. I'll draw it again if you haven't seen the last video. right? We have these 7 bridges. Each of the bridges represent one of the edges, and we had these 4 landmasses, which are each one of the vertices. And the question was, can you start anywhere on the graph and travel along and walk along each bridge exactly once? And now let's see if this is possible. So how do we do this? We want to find the degrees of each of the vertices and see, do we have all even degrees or all but 2 even degrees? Or if we're in the other case, then we know that it's not Eulerian, it's not semi-Eulerian. So the degree of this vertex is, of course, 3. The degree of this vertex, 1, 2, 3, 4, 5. Degree of this vertex, 3. Degree of this vertex, 3. We have 4 odd vertices. Our graph is not Eulerian. Our graph is not semi-Eulerian. No matter how hard you try, it is impossible to cross each bridge in Königsberg exactly once. Okay? Some of the bridges you're going to have to double up on. All right? So if we allowed ourselves to maybe double up on this bridge, okay, so this dash would say double up. Well, now our new degree of this vertex is 4. Our new degree of this vertex is 4. And so if we believe this theorem, it should be possible to find an Eulerian trail on this graph. And so let's see if we could find one. All right, so we want to travel along our graph, and we cannot repeat edges. The only edge we're allowed to repeat is this one that we've made the ghost edge of. All right, so maybe we start here in the middle, and we travel in this direction, and then maybe we go here, and maybe we go up and then down. So we're back where we started. Let's go to the right. Let's go to the left, double up on our bridge, and now we're up here. We crossed each bridge exactly once, well, except for the one we doubled up, and we did it. So by adding this kind of dummy edge, we made our graph semi-Eulerian. And so that's actually what we're going to be doing in the near future, is talking about how to Eulerize a graph, how to take a graph that was previously not Eulerian, not semi-Eulerian, and Eulerize it. This process has applications in 3D printing, for instance. Okay, so it's not just something that we do for the sake of doing it. There are actually real-life applications that involve Eulerizing graphs. Okay, and so that's what we're going to talk about in the lectures to come. But that's all I have for today. I hope you enjoyed the video. Let me know in the comments if you have any thoughts or concerns, and I will see you next time. Bye-bye.